This section here is really a review of system of equations, but you will be required to do a few things out of here. First of all, what is a system of linear equations? It's a system that contains two or more linear equations, and they will have multiple variables and multiple equations. So, for example, this system has two equations and two variables and is said to be a 2 by 2 system. This system has two equations and three variables. The variables are x1, x2, and x3, so that's a 2 by 3 system. And this system is a 3 by 3 system. It has three equations and three variables. Now, in practical applications like scientific or chemical reactions and more complex problems, like if you're trying to send a rocket to the moon or something like that, you could have quite a few equations and variables. So in more practical situations, you might have more variables and equations than you're going to see in this section. But I will pretty much limit the systems that we solve to three equations. There are three methods that you can use to solve systems of equations, and this is without matrices. You can actually graph the systems if they're only two variable systems, because if they're only two variable systems, then you can graph them in 2 dimensions. Three variable systems, you could try to graph them, but that would require some artistic talent to draw the three variable systems, so we won't try to graph three variable systems. You can solve systems also by the substitution method and also by the elimination or addition method. So let's start with solving a system by graphing. Now, you'll remember in the first module I showed you how to graph linear equations by plotting the x and y intercept. So to solve this system here, what we need to do is we need to graph this first line, 2x plus y equal 8, and we can do that by just finding the x and y intercepts. So if you let x be 0, then that would cancel out this term, and then you can see y would be 8, so that would be the point 0.08. And then if you let y be 0, that would cancel this term out, and you would solve this equation, 2x equal 8, and so you would get x equal 4. So we know that this line goes through the point 0.8, which is right here, and the point 0.04, which is right here. And so you just draw the line through that system, and that'll give you the line for the equation 2x plus y equal 8. Now the other equation, if you let x be 0 and solve for y, you'll get y equal 3. And if you let y be 0 and solve for x, you'll get x equals 9. So actually this one goes through 0, 3, which is right here, and 9, 0, which is out here. And then you draw the line through those points, and that gives you that line. And your solution is where they intersect. So you can see they intersect, and fortunately they intersect at a point on the grid here that's easy to define, because that point looks like it's 1, 2, 3 units to the right and 2 units up. So you can always check the solution to make sure. I can just plug the 3, 2 into both of these equations, and you'll see that it'll give me a true statement in each case as far as checking. Now, one of the problems that you have with solving a system by this method is, what if the intersection is not at a point that has integer values? What if it's at some value like 2.99 and maybe the y value is 1.8? Well, then it would be difficult to identify the solution simply by looking at the graph, and that's where those other two methods will come in. So we'll get to those later. When you solve a system that involves only two variables and two equations, there's three distinct possibilities. And one possibility is that the lines could intersect at one point given a unique solution. like the one that we just did. The one that we just did, when we solved this, we got the lines intersected at a unique point. When that happens, that's called a consistent and independent system. Now, the lines could actually intersect at infinitely many points. Now, when that happens, basically what happens is your two equations, like this equation and this equation, actually represent the same set of points. So in other words, these two equations actually identify the same line. So therefore, every point that's on the line is a solution to the system. And in that case, the system is said to be consistent and dependent. So it's a dependent system. And the third case is that the two equations might represent parallel lines, and if the lines are parallel, there's no place where they'll intersect, so there will be no solution. So if you have no solution, we say the system is an inconsistent system. And so you can see down here below each of these graphs, I identify the type of system that you have for each one of these. And so that corresponds to what I just told you about each system. Okay, let's take a look at another example. If you graph the line x minus y equal 3, when x is, let's see, what did I do? Oh, I found the x-intercept first. Okay, so when y is 0, x would be 3. And then when x is 0, y would be negative 3. So basically what you're going to do is you're going to see that that line goes through 3, 0, which would be right here, and 0, negative 3, which would be right there. So if you draw the point through that line, it'll look like this. And then if you graph the other one, when x is 0, y is negative 1, so it would go through here 0, negative 1. And then when y is 0, x is negative 1, so that would be this point right here, and then you draw the line through there. Now, I didn't use a grid paper here, but actually you probably should have used grid paper here, but if you use graph paper, you can see that this point of intersection here is 1 unit to the right and 2 units down. So the solution is 1, negative 2. And again, you should check that to make sure. Now, I want to finish up here with a statement about vertical and horizontal lines. If you graph the line x equal a constant, then that is a vertical line. And if you graph the line y equal a constant, then that would be a horizontal line. So for instance, the equation x equal negative 3 is a vertical line that contains the point negative 3, 0, where the graph of the equation y equal negative 3 is a horizontal line that contains the point 0, negative 3. So with that said, now let's take a look at this system. Here you have x minus y equals 3, so we know how to graph that. I think we did that in the last example. You plot the intercepts, so you get, this is the axis right here, so let me just identify that as the x-axis, and of course this is the y-axis. Okay, so the point 3, 0 would be right here, and then the point 0, negative 3 would be right here. So we know this line right here is the line x minus y equal 3. But the line y equal negative 1 would be the horizontal line that contains the point 0, negative 1. And there's the point 0, negative 1 right there. So you just draw a horizontal line through it. And then you find where the two lines intersect. And you can see they intersect at this point. And you can see here this is 1 unit, 2 units to the right, and then 1 unit down, and so this is the point 2, negative 1 is the solution for that one. So that concludes the section on solving systems of equations by graphing. In the next video I'll talk about solving by the substitution method.